Presentation title is Reconstructing Single-Cell 3D Genome Structures Based on Lennard-Jones Potential. Solve the sparseness problem of single-cell Hi-C. We use 2D Gaussian function to input the zero values, so we can remove the number of. It can assign some non-zero values to the previous zero values surrounding each one values. Imagine that the value 1 is located on the top of the hill, so the surrounding locations will have some non-zero values. I used strategy in this study. The institution behind this is that if two bits are in contact in the 3D space, their sequentially neighboring bits should also be close to each other in the 3D space. The Gaussian function we use in this research is PYP indicates the location of a single-cell Hi-C contact in the matrix. Mu2 controls the shape of the 2D Gaussian function. Xp minus I and Yp minus J indicate the x-axis and y-axis distances from a zero value to the location that has a single-cell Hi-C contact. We can use a parameter d0 to control how far the influence of the single-cell Hi-C contact can reach. A shows the curve of a 2D Gaussian function. B illustrates that the 2D Gaussian function can make the surrounding zero values of a single-cell Hi-C contact to be non-zero values based on the distance to the position that has a single-cell Hi-C contact. Each bit is put at the corner in the cubic lattice. The length of each cubic is 1. Therefore, sigma was set to 1 and Rm equal 1.122. When there is a single-cell Hi-C contact between bits I and J, delta Ij equal 1. Delta Ij is the imputed values based on a 2D Gaussian function, so the bit pair that have a single-cell Hi-C contact will have epsilon equal 10, which is the largest well depth at epsilon equal 10 delta Ij n squared. The institution is that the bit pair with single-cell Hi-C contact will have the deepest well, which is the hardest to be pushed off. The other bit pairs that have delta Ij less than 1 will have shallower well depths. Metropolis Hastings simulation was performed. A. The inferred 3D structure of the X chromosome of a mouse Th1 cell at 50 kb resolution when n in equation 3 equals 2. B. Each black dot indicates one single-cell Hi-C contact. The darker orange color indicates higher Euclidean distance parsed from the inferred 3D structure, and the white color indicates small Euclidean distance parsed from the inferred 3D structure. C. The distribution of the numbers of bit pair over different values of Euclidean distance parsed from the inferred structure when delta Ig equal 1. D. The distribution of the number of bit pair over different values of Euclidean distance parsed from the inferred structure when delta Ig between 0.7 to 1. E. The distribution of the numbers of bit pair over different values of Euclidean distance parsed from the inferred structure with delta Ig between 0 to 0.7. F. The contact probability of bit pair over different values of genomic distance. 2. A to D are the 3D structure of the X chromosome of a Th1 cell when Rm in equation 3 equals 8.976 and N in equation 3 equals 1, 2, 3, and 4 respectively. E to H are the 3D structures of X chromosomes of a Th1 cell when Rm in equation 3 equals 8 and N in equation 3 equals 1, 2, 3, and 4 respectively. A and I, the 500 kb resolution 3D structures of the inactive and active X chromosomes of a GM12878 cell, which is inferred by our Lennard-Jones method, respectively. E and M, the 500 kb resolution 3D structures of the inactive and active X chromosomes of a GM12878 cell, which is inferred by SCL, respectively. B, F, G, N are the 50 kb resolution structures corresponding to AEIM. C and D are the evaluations for A. G, H are the evaluations for E. K, L are the evaluations for I. O, P are the evaluations for M.